Have you ever wondered what's happening inside your computer when you load a program or video game? Well, millions of operations are happening, but perhaps the most common is simply just copying data from a solid-state drive or SSD into dynamic random access memory, or DRAM. An SSD stores all the programs and data for long-term storage, but when your computer wants to use that data, it has to first move the appropriate files into DRAM, which takes time, hence the loading bar. Because your CPU works only with data after it's been moved to DRAM, it's also called working memory or main memory. The reason why your desktop uses both SSDs and DRAM is because solid-state drives permanently store data in massive 3D arrays composed of 1 trillion or so memory cells, yielding terabytes of storage, whereas DRAM temporarily stores data in 2D arrays composed of billions of tiny capacitor memory cells, yielding gigabytes of working memory. Accessing any section of cells in the massive SSD array and reading or writing data takes about 50 microseconds, whereas reading or writing from any DRAM capacitor memory cell takes about 17 nanoseconds, which is 3,000 times faster. For comparison, a supersonic jet going at Mach 3 is around 3,000 times faster than a moving tortoise. So the speed of 17 nanosecond DRAM versus 50 microsecond SSD is like comparing a supersonic jet to a tortoise. However, speed is just one factor. DRAM is limited to a 2D array and temporarily stores 1 bit per memory cell. For example, this stick of DRAM with 8 chips holds 16 gigabytes of data, whereas a solid-state drive of a smaller size can hold 2 terabytes of data, more than 100 times that of DRAM. Additionally, DRAM requires power to continuously store and refresh the data held in its capacitors. Therefore, computers use both SSDs and DRAM. And by spending a few seconds of loading time to copy data from the SSD to the DRAM, and then prefetching, which is the process of moving data before it's needed, your computer can store terabytes of data on the SSD and then access the data from programs that were preemptively copied into the DRAM in a few nanoseconds. For example, many video games have a loading time to start up the game itself, and then a separate loading time to load a save file. During the process of loading a save file, all the 3D models, textures, and the environment of your game state are moved from the SSD into DRAM, so any of it can be accessed in a few nanoseconds, which is why video games have DRAM capacity requirements. Just imagine, without DRAM, playing a game would be 3,000 times slower. We covered solid-state drives in other videos, so in this video we're going to take a deep dive into this 16 gigabyte stick of DRAM. First, we'll see exactly how the CPU communicates and moves data from an SSD to DRAM. Then we'll open up a DRAM microchip and see how billions of memory cells are organized into banks, and how data is written to and read from groups of memory cells. In the process, we'll dive into the nanoscopic structures inside individual memory cells and see how each capacitor physically stores 1 bit of data. Finally, we'll explore some breakthroughs and optimizations, such as the burst buffer and folded DRAM layouts, that enable DRAM to move data around at incredible speeds. A few quick notes. First, you can find similar DRAM chips inside GPUs, smartphones, and many other devices, but with different optimizations. As examples, GPU DRAM, or VRAM, located all around the GPU chip, has a larger bandwidth and can read and write simultaneously, but operates at a lower frequency. And DRAM in your smartphone is stacked on top of the CPU and is optimized for smaller packaging and lower power consumption. Second, this video is sponsored by Crucial. Although they gave me this stick of DRAM to model and use in the video, the content was independently researched and not influenced by them. Third, there are faster memory structures